days. I hope you are well in the mood for the first session of the CAiSE'21 conference. Unfortunately, we are running it online, not physically here in Melbourne, but nevertheless, we hope we will be able to produce the best value and high level of talks through the conference. So very warm welcome also from me, Martin Poliviani. I'm senior lecturer here at the University of Melbourne, and I'll be chairing this first session. So we have three exciting talks lined up. So the first talk will be by Simon Hacks, and he will present us their work on entitled Towards an Ecosystem of Domain-Specific Languages for Threat Modeling. So Simon, while you share your slides, I will also invite everyone to post questions through chat or prepare questions and then raise their virtual blue hands, and we will have a discussion after the presentation. Simon, so the floor is yours.
Thank you for the introduction. Yesterday was a bad day for someone from Germany living in Sweden, so both teams lost. So nonetheless, I will try to give my best on this presentation, which is called Towards an Ecosystem for DSLs for Threat Modeling. And I wrote this paper together with Sotirios Katsikeas, who is a PhD student in our group at the KTH in Stockholm. And yeah, my name is Simon Hacks.
Simon, wait, we don't see your, I don't see your slides yet.
Okay.
Are you sharing your slides?
Yes, I can try to reshare.
All right, sorry for that. Yeah, now I can also see them. Sorry for that.
Okay, great. You didn't miss anything. As I said, my name is Simon Hacks. I'm a postdoc at the KTH, and yeah, I will talk about ecosystems. Before of that, I like to motivate a little bit the topic. So the people who have seen my presentation yesterday at the MSAT, they might already know the slides. So we're living in a more and more connected world. And if you are very keen to new technologies, you might have some IoT devices even at home. So maybe your toothbrush is already connected to the internet. And yeah, so we are connecting more and more of our stuff to each other through the internet. And it's not just that we do this as private persons, but also companies do it this way. They connect their facilities to the internet so that the people can work from home, for example. And this causes also some security issues. For example, in the Ukraine, we have seen 2015 and 16 attacks on the power grid, and it's not very nice if the power is missing during the winter when it's cold, especially if you're heating with electricity. But even our entire life is depending on energy consumption meanwhile. So if there's a report in Germany which says after a power outage of a week, there will be catastrophic results in Germany going on because all the supply chains don't work anymore, you don't get any food and so on. So we need some kind of techniques to help or to assess that the infrastructure that we are operating is secured. And what we do in our group is we develop threat languages which we can use to assess if the systems are secure. And we have a framework called the Metaattack language, which we can use to model such systems. And the Metaattack language is basically going back to attack graphs, where we have two kinds of nodes. We have end nodes and OR nodes, which are the fundamental building blocks of such attack graphs. An end attack node means that we have some kind of parents to this attack step, and both of those attack steps needs to be fulfilled so that we can get to this step here. Being more concrete, imagine you are living in an apartment and then some bad people want to get into your apartment and to get into your apartment, they need to come through the door. This is one of those one, and the other one is they need to take off the alarming system. So you need to fulfill two things to get into your apartment. On the other side, we have all attack steps, meaning that just one of those attack steps needs to be fulfilled. So for taking again this example of an apartment, you can either come in through the door or through the window. Yeah, and that's what an attack graph classically describes. And then we model from the attack surface to the point where we want to go to. So, for example, an attacker is interested in to get the jewels out of my apartment. And yeah, so we model the entire way and the different ways an attacker can follow. And that's the classical way of attack graphs. And additionally, we have defenses, meaning we can introduce some means that hinder the attacker to perform a certain attack step. For example, yeah, applying better locks on our door. To do something with our attack graph, we have also something called time to compromise, which describes how much time an attacker needs to spend on a certain attack step. We are classically using probability distributions because you are never very certain that it's exactly 1 hour, but we can say, okay, 10% of the attackers do it in 1 day or something like that. And we have the same for defenses, where we can say, okay, the defense is that likely to be in place. What's now special for the meta-attack language is that we take those attack graphs and split them down into assets, which are logical constructs, grouping things together like a Windows operating system. And each of those assets describes a certain part of those attack graphs. And then we take those assets and provide them as a portfolio to the end user. So the end user itself, they don't need to have any security knowledge anymore. And they just need to know, okay, we have here asset A is talking with asset C, and we have a connection to asset B, and so on and so forth. So they just need to know how their architecture looks like. And inside, we then can see that we have our attack graphs, and then they follow the associations between the assets. And so we are combining again the single attack graphs to a bigger picture. And then we can perform our simulations on this. And that's something we do in our group. So we are writing a lot of languages that are codifying the security knowledge, and then we can provide it to the end user. As I said, now the big question is we have a lot of languages, and we recognize that for some parts we are inventing the wheel over and over again. So we are having same concepts in different languages, and that's not optimal because it's time that you need to spend. And yeah, if you think about that we get to some kind of certain patterns, which could help the other language engineers as well. So what we propose in this work is to use some kind of an ecosystem of those languages that we have, so that they can build on each other. And first of all, we like to think about what are the properties of an ecosystem. And there are 4 of them, and that we have identified. And the first one is that each ecosystem has some kind of stakeholders. They are platform sponsor, complementers, and consumer. The platform sponsor in our case is Forestity, a spin-off of our group. They are developing the MAL compiler, meaning we write those languages and then they are translated to Java code. So they provide us somehow the tools that we need to do our language engineering. Then we have the complementers. In our case, these are the language developers, so PhD students in our group, but also people at Forestity developing languages for their customers and so on. Then we have the consumer, so that are the people that are interested in doing the security analysis of their systems, and they are taking those languages and use them to model their environment. Then a property of an ecosystem is to reuse and combine the components that are part of this ecosystem. So we are not just developing languages for one certain partner, but we want to have some kind of generalization in those languages so that they are provided and reused in different domains as well. And an idea is that we have languages and can combine them. For example, if we have a look at your classical office IT, like you have Microsoft Office running with Word and Excel and such stuff, that you have those parts that are most probably in all kinds of organization present. Then you have also some kind of assets that are very specific to the domains. For example, for my case, it's often the power domain. So that you talk about SCADA systems and so on, and then you want to have languages, which is also for that part. The third property of ecosystems is the free use of the components. Here are languages, so there should be no restrictions that you are not allowed to combine certain languages, for example. So this is from the user perspective. And then from the developer or language engineering perspective, we need some kind of an alignment structure. So some kind of framework telling the language engineers what they should consider in developing the languages so that the languages are combinable with each other. But at the same time, we need to have some kind of an autonomy to the developers that they are not forced to too strictly to follow certain patterns. Okay, so that are the properties, and then based on these properties, where we are thinking about the languages that we are having in our group and which we are using, and we come up with some kind of a hierarchy of languages that we propose should be developed. So, for example, there's also a paper on Golang, which is a language which we use to codify classical parts that you can see in all IT-related stuff. So meaning that you need some kind of hardware and you need some kind of software which is run on that hardware. Then you might have some kind of vulnerabilities that can be used by the attacker to be exploited. And then you have also some kind of networks where things are communicating with each other. So things that are in place in several concepts. And then we have this central calling, and then we specialize it to other domains. So for example, we can go the path to IT languages, where we are talking about maybe server environments, so about Linux servers, where you can have Ubuntu and so on, where we then model specifically what are the classical vulnerabilities of an Ubuntu whatever version. And we can do it for different things. And then we can also have this OT part, where we are looking more at the industrial side, and then for example, go for ICS lang, meaning we are looking at SCADA systems and such stuff. Then we can even go further and specify those languages that they fit more to the power domain or the gas domain. And then the idea is that the people using those languages can see, okay, in my organization, we have office IT, we have some servers. So I'm taking this language and that language, and I'm a transmission service operator. So I take this transmission lang, and then I combine those languages and can model my entire organization. Then we have also the idea to model not just IT things, but also physical threats, for example. But this is future work and a vision where to go. Okay, now we have this idea how we should develop our languages and how we can combine them. Now we have different cases how we should maintain our ecosystem. And the first case is that we want to have we have a customer and we recognize, okay, we need a new language because it's not already present and because there was nobody thinking about this before. And if we are looking for such a language, we should first check if there is maybe the possibility to combine those different languages that we already have at hand and use one of those or the combination of them. If there's not this possibility of using an existing language or combining language to serve the needs of the user, we are in the need for a new language. And therefore, we then should traverse this hierarchy that we have and think about where should we position this new language. And therefore, we take a look at the different abstractions that we have and should search for that layer where we think, okay, here we have most of the needs already covered by our customer, but we need to have a new language that is tailored to this new domain that we are looking at. Another thing is that we want to maintain our existing languages. And if we think about, for example, new assets. So we have a language and then we recognize, okay, we have the need for a new operation system in the server length. So there's a new Linux or something. Then we could simply add this to the server language or language B here in the case. But to some degree, so concrete operation system is something very special, but there are also some kind of possible abstractions. And if we recognize this concept in also another language, then we should think about, okay, maybe it's worth it to move it above to a language which both of those more concrete languages inherit from. But it could be also the case that these two languages have some kind of an abstraction that is not already covered by their mother language at the moment. So we might be also in the need for introducing a new abstraction language and insert it in between the inheritance hierarchy. And then the case 3, so I was talking about combining different languages, and there are different possibilities to do it. In our PowerLang paper, we said that we are using the inheritance hierarchies to link those different languages to each other. And this is from a software engineering perspective no good idea because we are creating strong coupling between those languages. Therefore, in this paper, we also propose something like a linking language. So where we have a language that is specially designed to do the traversion from language A to language B. So we are trying to get a loose coupling between those languages. Okay, future work. The ecosystem itself, it's not evaluated. If somebody has some suggestions how you can evaluate such a construct, please let me know. Otherwise, we need to have a look at the time and see how the people develop the languages and how they build on each other. And yeah, use the time as evaluation. Then for this linking languages, we have the problem that to do it in a good way, we need something like multiple inheritance, which is at the moment, unfortunately, not supported by the compiler. So that's something we should go into this direction, or some other concepts that we can use to get those two different concepts into of two languages into one single language. Yeah, and for the language development itself, we are at the moment developing an approach. We did some interviews with language engineers in our group and so on to distill how they develop the MAL languages, so that we have some kind of guidelines that are in line with our way of building the ecosystem, to ensure that this this guidance, the alignment of the developers is on the point on how to develop the languages. And that concludes my talk, and I guess I am perfectly in time. So I'm looking forward to your questions.
So thank you, Simon. Yeah, perfect timing. That's right. So if you have questions, please post them via chat function or raise your hand and I will unmute you.
Okay, so one thing I can mention is also the generalization. So at the moment we are just looking at the MAL language itself, but I think there's also the possibility to generalize it to DSLs. So general, if you have a look at our related work in the paper, you can see that often DSLs are built from scratch. And I think it's worth to think about, okay, more about reuse of DSLs and the concepts that are already codified where possible.
Yeah, that was definitely my first question when I read your paper, right? So how general is a framework, how applicable it is to other domains and other domain-specific languages rather than attack. So, but what would be the effort, right? Kind of, is it readily applicable, or you really need to adjust and rethink some components of the approach of the framework?
I would say the idea of an ecosystem for other DSLs is, it's just an idea. You can just take it and think about it. The main issue is that you need to have DSLs which allow to be linked to each other and that they build on each other. So if this is not possible, it would be complicated to build such an ecosystem.
Mm.
But
so some common core between the languages.
Yeah, right. So what you can see is that, for example, usually the DSLs that build something like this, there's just two kind of layers or something, and that's it. So we are looking for a bigger picture.
All right. So I'm checking if there are some other questions. I don't see them at the moment. Maybe I can post another question. In the paper, you also give examples how you introduce a new language that fits the framework, but I also was puzzled a bit, like how do you decide, like where is the boundary that you need to introduce a new language? Is it some technological component, let's say, that you need to protect and you need to design some specific elements to model the attack on that component, or right? So is it a goal to have many languages, or the goal is kind of later to collect them and have learn from this activity and then design overarching language? So what is the big goal here?
Yeah, so the big goal is that I wouldn't say that we should have a lot of languages, but those languages that you need to express classically what you have in the organizations. And so basically you have this path going to the IT side and then maybe some OT stuff. And hopefully then it's mostly done. And when we are talking about introducing new languages, it's also about often just terminology. So if you look at the OT domain, there are often, depending on which concrete domain, different names for the same thing. So some people call it RTU and other call it PLC, but at the end, from a technical or threat modeling perspective, those things are the same. So you could model then this common behavior of those things and have a look at what time the people need. And then you would specify just a language which adapts the certain domain phrases that they're using, for example, in power or in gas or in cars. Yeah, I don't know if
Yeah, I see. Well, I kind of understand the process, right? Maybe yeah, there's also some light that you just brought on the end goal is helpful. I see a question from the audience. Yanis, I will unmute you, and so I'll allow you to talk. Please ask a question.
Hello. I would like to kind of maybe comment on that. When we talk about ecosystems, I think it is important to talk about the actors in the ecosystem. And it seems to me that in this case, the actors are the people and the organizations developing, using, contributing to the languages. It's not the languages that are actors in this ecosystem. And I think if we talk about sort of survival and of languages and modeling languages, then it is the sort of user or the ecosystem engagement in them. Can you a little bit comment on this aspect of your work?
Yeah, I fully agree. So in our work, we are focusing on the languages because we are technical people, but we have on the one hand side, from the contributors, obviously the Forestity company developing the compiler, and I'm, for example, always as a language engineer talking to them that we need this multiple inheritance. So it's also some kind of relation between the people to convince them that there's something from the language perspective that we need, but they need to have the time to develop it. And then there are also the customers that use our languages, and I have some restricted access to them, but there are consultants in Forestity especially that take those languages, go to the customers and model with them together how the architectures look like, and then they get also the new demands of them, like yeah, we would like to model this and that, and this doesn't work, and then the languages within the ecosystem needs to be further developed. But yeah, there will be also a lot of this human interaction things that should be considered, but I think I'm maybe not the right person to do research on this one. Does this answer your question, Janis?
It does. Thank you.
Okay.
All right. We have time maybe for one more question. Anyone from the audience? All right, maybe I can have a very quick question, last question. So, like imagine you develop a new language, right? So how do you come up with the primitives for that language? Again, in the paper, give example of proposing a new language to protect some technological component. Don't remember now which one, but then how do you ensure like expressiveness of that language, that it's right, it serves a purpose, you can express all different attacks that can be envisioned, etc. So maybe.
Yeah, so there are different ways to do it. So one way to do it is to take standards that are around. For example, the SCL standard is about the protocols used in substations in power domains, so TSO and DSO. So we have a PhD student, she took that standard and make sure that all the components named in the standards are in the language itself. Then there are not like standard sources. This was also a question yesterday. The MITRE standard, for example, if you might know it, they are defining a lot of different tags that you can use and on different kinds of assets. There's something for enterprise, for mobile, for ICS. And what we're partly doing is we're taking our languages and evaluate them against the MITRE standard and check, okay, is this included what you can express in MITRE? And then you, of course, can also go directly to the domain experts, do interviews with them, and check, okay, what would they like to model? And then you do some kind of a literature review and see what are the possible attacks on the CAN bus in cars, for example. Or and what we are also doing is we are doing our simulations and check them against real world happenings. So can we model how the attack on the Ukrainian power grid was done, or we do our simulations, and let's also security experts do an assessment, and then we check, okay, are the results of our simulations likewise those that the experts did?
All right. I see. Thank you very much, Simon. For the sake of time, I propose we conclude the first talk. Thank you for your presentation. And let's move on to the second one. The second one will be by Martin Kabierski, right? And he will present their work on privacy-aware process performance indicators, framework, and release mechanisms. So Martin, when you're ready, the floor is yours.
All right, you can hear me, right?
We can hear you well, yes.
Okay, perfect. Okay, then yeah, thank you for the nice introduction. Like Artem said, I'm Martin, and I will present the results of the joint work with Stefan Franco Petersen and Matthias Weidlich on the topic of privacy-aware process performance indicators. So, oops, now, next slide. Yeah. So just to give a little bit of motivation, what are we talking about actually? So if you have like your information system and you're modeling all your fancy business processes, you want to actually improve upon them, and you want to monitor them, and you also want to analyze them to, for instance, see where are certain bottlenecks in your processes or in your company at all. And one way to actually quantify this is to use as so-called key performance indicators, or short KPIs. And what these actually are is they are measurable goals set by the management onto the process owner and the processes or the process workers, which they should fulfill. And the idea is that management says, okay, if we fulfill these goals or reach these goals, then we as a company will grow. And there are a lot of different sorts of KPIs, and one particular subset of KPIs are so-called process performance indicators here on the left side. And what is so special about them is that these can be defined and evaluated solely on the basis of recorded process instances. So you don't need other sources, you don't need some review sites or some questionnaires to customers, but you can actually just define them on a process level and analyze these automatically just by the recorded process executions. For instance, if we look at this insurance claim process on the top left, we could define these three process performance indicators. The first one would be the mean seizure time of our process. The second would be the percentage of rejected claims. And the third would be the mean damage payments in a week. And we could have target values for these, which our workers should reach for us as a company to be good in some sort. So if we now look at this use case of analyzing PPIs, and actually frame that in the, from a perspective of the data flow in our information systems, we see different phases. We see we're capturing data upon execution of the process. We're using it for our primary use. We are storing it persistently, and at some point we're deleting it. But also we have the PPI use case as a secondary use case on the stored data sometime after it has been used for its primary use case. And the thing is, we have a not so new privacy regulation in the EU, which actually says, the EU GDPR says that data analysis on original recorded data beyond the primary use requires the consent of the recorded individuals. This may be troublesome. Why? Because usually in these processes, we are recording data of some people who actually executing the processes are related to them. And we would need the consent of these people every time. And on the other hand, also by doing such a PPI analysis, we may cause negative, negative things for the people that were recorded, and for which we actually saw in those PPI results that they, for instance, had a pretty bad performance. And this is something the GDPR wants to protect the people. So what can we do now as the process owner? well, we could either not calculate PPIs at all or use anonymization techniques, which actually destroy the link between the single recorded individuals and the recorded PPIs, or the analyzed PPIs. So, and one way to actually do that is through a technique called differential privacy. And what this actually does is it gives us a controllable privacy guarantee for aggregations, like process performance indicators, which essentially are just aggregating numbers to one number of a lot of recorded process instances. And we do this with a privacy parameter called epsilon. And what differential privacy actually does is it says, well, we have one true result for our recorded executions, but let's just obfuscate that result. So let's throw some noise onto it, and then also throw noise on it in such a way that for neighboring input sets, we cannot distinguish anymore whether certain inputs were existent or not. So to give a little example for that, we have two Gaussian distributions down here, and we have two input sets, x1 to x4, and another time x1 and x4 again, but in the second time we are omitting x2 from the result. So, and the obfuscated output result probabilities which we get, these distributions are very similar. So we're not only not getting the true result anymore, or only in for a limited amount of executions, but we're also limiting how much we can see whether that value x2 was actually part of the original data or not. So this is good, because now we can actually do analysis over all individuals without actually showing off the impact a single individual has. So what can we do with that? Well, oh yeah, first of all, of course, we are obfuscating results. So we have a trade-off between the result accuracy of our result and the esteemed privacy protection we have. And we can again control that through our epsilon. So, and what we now did is we wanted to include this privacy protection technique into this PPI calculation settings. And what we came up was this centralized framework, which essentially looked a little bit similar to the slide, to the illustration we saw a few slides ago, but we added this PPI interface. What does it mean? Well, we separated our whole environment into a trusted and an untrusted environment. And for instance, in the trusted environments, all the data flow is pretty much the same as it was before. So for data capturing, promise, data deletion, every steps may get onto the true data storage on the original recorded data. They may use it. But all these secondary use cases, like in our case, this PPI querying, does not access the true data storage anymore, but instead it accesses this PPI interface. And what this PPI interface does is it receives PPI queries, it calculates the true query result on the data storage, but does not return that, but instead adds this controlled noise onto the result. And it also has some other mechanism that actually cause us to ensure that privacy is remained over a longer period of time. So, and by doing that, we're actually allowing the analysis of PPIs in a privacy protected manner. So that's nice and all, and we now have this PPI interface, but what still needs to be answered is, okay, how do we actually define PPIs in a way that we can use differential privacy on it? And how can we actually also do that without a lot of quality loss? Because still we want to have an analysis which actually gives true or reliable results. Otherwise, the whole process is worth nothing. So, and what we turned to for that, first of all, for the definition of PPI was the so-called process performance indicator notation, short PPNO. And what this actually does is it says, well, we can build complex PPIs, arbitrary PPIs taken from these processes by using small building blocks. We can see here in the slide, we have so-called single instant measures and multi-instance measures. And what these measures are is they are these basic building blocks. So all these single instance measures, they actually take data from the process executions directly. So we can, here on the bottom line, you can see we can measure time instance between two activities. We can count things that happened in the process. We can check for certain conditions in the data in our process, or we can actually retrieve data of attributes in our process, in our recorded processes. And using these base measures, we can then aggregate these in multi-instance measures using aggregated measures. These are well-known functions with known semantics, like a sum function or mean function or minimum or maximum function. And then as a third step, we also have so-called derived measures for the case where you need to define complex arbitrary functions, which may be defined on single or multi-instance measures. And to give a little example for that, we can how we can compose the PBI from these building blocks. For instance, let's say again, we have our insurance claim process and we have our PBIs on the right side, and we want to calculate the percentage of rejected claims. So now assume we have 4 process instances, 16, 17, 18, and 19. These are the identifiers. And now what we could do, first of all, for each of these process instances, we could count how often a claim is rejected. So this will give a binary value. Either it is rejected or it is not for each of these process instances. On the right side hand, we just count how often, how many process instances we have. So, and now for each of these sides, we can aggregate them using a sum aggregation measure. So on the left side, we get 3, and on the right side, we get 4. And then we can further aggregate these using a derived measure with this equation, which essentially converts the fraction of the left side to the right sides into a percentage value. And this way, we build a complex PBI out of these building blocks. So how can we now get privacy protection into that? If we think about what differential privacy actually achieves, if it allows the protection of aggregations over multiple values without leaving information about the singular values. So when we look at this tree, we can see, okay, for instance, these 2 measures here, these aggregation measures, they do exactly that. They aggregate multiple values into one new value. Or another option would be that one. This one also aggregates multiple values into a single value. And if we now can assure that if we privatize, for instance, these 2 aggregation measures, then these cover all the trace level information we gathered from the traces through the single instance measures and privatizes them. So if we have such a tree and pick multi-level functions in such a way that all of the single level functions are actually covered and privatizing these functions, we actually get differential privacy. So, and if we look back at our function, at our PB graphic here, we see again all these multi-instance functions. These are applicable for differential privacy. So the question now is, okay, if we have such a tree and if we have selected our functions, if we have selected our sum, mean, min, and max functions or our arbitrary derived measure function, how can we now achieve differential privacy for these? And what we did in our paper is we proposed multiple so-called release mechanisms that introduce differentially private noise into these. For aggregation measures, we proposed 3 measures, one based on the Laplace mechanism, one we called the interval-based mechanism, and one called the threshold-sensitive mechanism. And for derived measures, we actually proposed a 4th one because the 3rd just proposed are not applicable in that case. And they contain a lot of math, and I will skim over that and just show you real quick the basic idea of these measures. So, as I said, the first one was to say, okay, let's privatize these aggregates using the Laplace mechanism. And what the Laplace mechanism is basically just saying, okay, we have a Laplacian probability distribution with a certain set of parameters, and we're calculating our result, drawing one value from that Laplace distribution, adding it onto the noise, and this is a noisified, obfuscated, differentially private value. And we make this differentially private by using this shape parameter B, and this is built by introducing the privacy parameter epsilon and the so-called global sensitivity of the function we want to privatize. Because again, I said in the beginning, differential privacy obfuscates the difference between singular entries in data sets. And this global sensitivity captures exactly that. We use this to pretty much decide what is the maximum impact a single value may have on our result. And in the paper, we concluded that for the 4 aggregation functions, these are the global sensitivities. So x with an upper line is the largest value in our input sets, with a lower line is the lowest value in our input set, and v is the cardinality of our input set. And using this, we now have one mechanism for the privatization. So the problem with using this Laplace mechanism is that it has this high sensitivity, That means that the results we get were actually very noisy. We have large fractions of noise, which makes most of the results not really usable. And another way to circumvent that is to use the so-called exponential mechanism, which is another mechanism that provides differential privacy. And what it does, it allows the privatization of arbitrary outputs, not just numerical values, by using so-called score values. So and our idea was we want to reduce the input side by grouping all the possible outputs into intervals. Then we sample one of these intervals using this exponential mechanism. And from that interval, we just sample an output uniformly. And just to give a quick idea of what we're actually doing here is, let's say we have an input set of the values 2, 3, 7, 8, and 10. And we now would build for each of the aggregation functions based on these inputs, these intervals. And these intervals are built in such a way that the exponential mechanism has very low sensitivity and still provides these privacy guarantees. And using these intervals, we can now build a probability distribution over these intervals, choose an interval just by sampling one from that distribution, and then we just sampling one value from this interval. And what actually happens is that this approach actually guarantees lower sensitivities than the Laplace mechanism, which we will see in a bit later when I talk about the evaluation. So a third mechanism we proposed is the so-called threshold sensitive mechanism. And the idea is to say, well, we know that the exponential mechanism allows arbitrary inputs to be privatized. And if we look at what we actually want to do in our PBI case is that we want to compare the results of our PBI against the target value to see whether the goal has been reached or not. So here, that's this column in our table. And the idea is to say, well, what if we don't take exactly this information into our scoring function? What do I mean by that? Let's say we have the input set again of 2, 3, 7, 8, and 10, and we're using a sum function for aggregation. So we've just seen how the interval would look like in a normal case. And now we say, okay, the target function, which we want to compare this PBI again, would be, for example, that the value should be less or equal than 30. Then we could, for all outputs that signify a wrong outcome with respect to that target for our input, reduce the likelihood of these outputs. So if we see, we have our input, if we sum this together, we get 30. For 30, we know that 30 is less or equal than 30. So these input would actually reach the intended target value. So all the values in our output, we can see on the left side of the blue line, which is our target value, now have higher output probabilities than all the values on the right-hand side. And by doing this, and just then sampling again with the probability proportional to these interval scores values, we now have a mechanism that actually takes into consideration the target value and tries to preserve the information gained from that data while still giving these privacy guarantees. So these are the three mechanisms we have for our aggregation measures. And just real quick, I will also talk about the mechanism we propose for our derived measures. And there we use the so-called subsample and aggregate framework. Why do we have to use this? I said in the beginning that these derived measures may have an arbitrary form. So to use all these mechanisms we just proposed, we need to know the sensitivity of the functions, which was pretty easy to pinpoint for sum and mean and min and max, but for arbitrary functions, we may not know this in advance. So all these introduced mechanisms are not usable in this case. But there is a handy framework, which is called the subsample and aggregate framework, which says, well, you could calculate the result on subsamples of your data normally, and then aggregate these with a known function afterwards. So to give an example, let's say we have these 10 values, and we can now put them into 4 buckets with 2 values each. Now we would calculate our usual function, which in this case here is a mean function. And then we still need to add privatization into this. And we do this by now aggregating these values with a privatized function and are now able, because of this, to privatize the results of this derived measure without knowing its sensitivity. So these are the 4 mechanisms we showed. With this, we are able to properly privatize all these multi-instance measures in our tree. So now, of course, the question still holds, okay, well, how good does it perform? It's nice we have these, but if these perform worse, then we can't use these in practice, actually. So, and of course, we evaluated everything. And what we did is we used the Java-based implementation of the PPNO framework, which is publicly available, and extended it with our privacy protection. It's publicly available for anyone to use and extend. And we did two things. First of all, we did controlled experiments to assess the impact of certain input specifics on these different release mechanisms. So we tried different distributions from which data comes. We tried different input sizes. We tried different input parameters. We tried all the different mechanisms. And then we also did a small case study on 6 PBIs, which we defined on the publicly available CAiSE' event log, which is an event log from an emergency department, to see whether these also would hold in settings where we try to calculate PBIs over a long amount of time. And I will just skip over a few highlights of these evaluations because time is running out. And first of all, for our controlled experiments, I think the most important step is how well do these approaches work under different privacy parameter instantiations. And what we saw is that the interval mechanism on the left side, on the left two plots, you can see this is for the minimum and maximum function. You can see that this interval mechanism completely outperforms the classic Laplace mechanism. So our assumption that the sensitivity is too large to be applicable was true here. And on the right-hand side, we could also see how both Laplace and interval mechanism performed for the mean and sum functions. And there we could see that the Laplace mechanism performed better for larger values of epsilon. Another highlight of the evaluation was the applicability of these threshold sensitive mechanisms that took the target value into account. And what we did is we used this mechanism on target values which were a little bit smaller or a little bit higher than the true result or calculated on the input set. And what we saw was that this threshold sensitive mechanism actually pushed large fractions of the output probability mass onto the side which preserved the information whether the goal was reached or not. So this is really good because this means that we can actually take this into consideration during privatization. And then as the last highlight, of course, we did the case study, which I already told, on the disastrous cases log, and we compared our results against the results we achieved using the Preble algorithm, which is a log anonymization technique, which anonymizes logs and then doesn't need a specific anonymization technique anymore for the calculation of PPIs. And we built 6 PPIs on that data set, which were taken from other publications, and try to measure over time how well our approach worked against the true result. And just to show the results for the first PPI, which was the average waiting time until the admission of patients in this emergency department, on the left side, we could see that we were generally able to reproduce general trends in the data. Of course, we have noise in there, and we have certain months in which the ratio of the noise or the variance is pretty high, which is because this log contains only 1,000 cases. So if you see we have a time span over 2 months, this means there's roughly 50 data points each month. So, and in some months there are not so many. So in these cases, of course, the variance in our results will be very high. And then comparing these results to the Preble algorithm, I chose this PBI1 because it's a time-based measure. And we could see that the Preble algorithm, which uses time shifts to actually anonymize the timestamps of the process executions, actually had a cumulative error over the time, so which made it completely unusable in these use cases. So in comparison, we performed pretty good here. Okay, I will skip over the last one. We had comparable results for all the other PBIs as well. And due to time reasons, you see them in the paper, and you also can see them in the public repository. There is a lot of more of them. So to conclude, what did we now do? We did a lot. We, first of all, introduced a framework for the centralized anonymization of PBI queries, which was this one down here, where we introduced this PBI interface. Then we instantiated this framework with different release mechanisms to achieve differential privacy based on the PPNO meta language and this concept of these function trees, which we were prioritizing. We proposed different release mechanisms for this framework and evaluated us using these mechanisms, using artificially generated data and a case study. And the results indicate that this is indeed, given that we have enough data points, shows applicability in real life. So for future work, we intend to actually recommend functions to privatize in the function tree. At the moment, we are still cherry picking which one we want to privatize. And this, of course, is something we would like to automate in the future. So with this, I conclude my presentation. Thank you very much for your attention, and I would be very willing to answer any questions.
Thank you very much, Martin. Nice presentation. I think we have time for a couple of questions. Questions from the audience. There is a question from Simon. Yeah, please.
Yeah, thanks for the presentation. Very interesting work. It's not so deep into my knowledge, but there's something called k-anonymity. So did you compare your work to which degree so what k you have with what you're doing?
We did not do that, and we made a lot. It was a big decision whether we actually want to took the route of differential privacy or k-anonymity. But the thing is that essentially you have two settings. And the thing with differential privacy is differential privacy fixates a query and says, okay, we're privatizing the query and we can throw in changing data in there. So whereas k-anonymity says, okay, we are privatizing the data. So k-anonymity needs a static batch of data, privatizes that data, throws out one batch of privatized data, and then you can do analysis with changing queries on it. And the thing about that is that that does not really allow a monitoring. So you would need batches of data which you're privatizing, and if you change anything about that data, you, in the worst case, would also have to privatize that, taking into account the original old data which you have already privatized. There are some extensions of k-anonymity. I think it's uniqueness, which essentially try to tackle that problem, but they also, I think, have exponential runtime. And the good thing we have here is that this privatization of using differential privacy is rather fast. So we can almost do a real-life monitoring using these values.
Okay, thanks.
All right, I think Shazia was next with a question. Shazia, I will allow you to talk now.
Thank you. Martin, thank you very much for your presentation. It's very interesting work. I just wanted to get your take on data sparsity. You know, if you are trying to apply these mechanisms on very sparse data sets, what do you think will be the results over there?
Yeah, let me go back a little bit onto the point, I think, which brings this across the best, which was our interval-based mechanism. So what we also evaluated was, I said in our evaluation with the artificial data, we use different data distributions and different sample sizes. And we did this to evaluate exactly this. And in the paper, there's a bit more about that. And what we essentially found is that different functions we actually use in this PPI context, for instance, for these aggregated measures, where minimum, maximum, mean, and some functions were the ones available, had different behavior under these sparsity constraints. So for instance, what we did in this interval-based mechanism was that these intervals are chosen so that one interval contains exactly one data point. So that essentially means if we have a very sparse data set with a large domain, let's say we have one very small value and one very large value, then you have two very huge intervals for which you're sampling. So essentially, you're, in this case, sampling just from the whole space again, or you're sampling from half the space because you're choosing uniformly a value from that. And this is a problem for the minimum and maximum aggregation. For the mean aggregation, it is not so much a problem because we were able to build these intervals in a different way, which was not dependent on the distribution. For some, similarly. So depending on what data distribution you actually have, the performance of these indicators will go down or up, or the expected result variance. Yeah, I hope, did that answer your question a little bit better?
Thank you.
Okay.
All right, there is one more question in the question and answer section by Gamal. Gamal, if I unmute you, can you ask your question in voice, or do you want me to read this question?
Ah, there it is. Okay, let me see.
Okay, maybe I can read the question. I didn't see Gamal. The value of epsilon depends on the range of values to be anonymized. For example, the epsilon of 1 for a range of 0 to 10 is different from for epsilon of 1 for a range of 0 to 100. Could you explain how you quantify the epsilon value in the proposed mechanism?
Yeah, that's a very good question, because of course, since this epsilon value actually just protects neighboring data sets, of course, it would have to obfuscate way more data for range 0 to 10 than for data in the range of 0 to 100. We actually, in our evaluations, if I go back to the overview, we actually, for our project, just show static privacy parameter. The good thing, especially for these PDI evaluation settings, was that despite a few months where we had sparse data only, or only 3 to 4 data points, the number of instances during these months was actually around 40 to 50. So we didn't actually have this problem. I think that's a very good question, and something we should definitely look into. So we just fixed the epsilon, and differences actually came through different sample sizes, different distributions, and different the difference mechanisms, and how the sensitivities for these functions were actually instantiated. So I think it's a very good idea to actually look into that in the future and see how we could quantify the reliance of the privacy parameter on the input size or the input range.
All right, thank you, Martin. I propose that we take further discussion offline and we move to the next speaker. Thank you very much, Martin. So we have one more presentation by Karam Buchaya. I hope I pronounce this correctly.
Yes.
So, Karam, can you please share your screen, share your presentation slides? So yes, the talk will be on PSG approach, which is a stochastic gradient descent solution for privacy preserving during protection transitions. All right, yes. Karam,
thank you,
please,
Arsen.
the floor is yours. Yeah, please.
Okay, thank you. Well, good afternoon, everyone. So my name is Karam, and I'm going to present our research work entitled PSG, a stochastic gradient descent solution for privacy preserving during protection transitions. So I'm working with Richard and Philip from the LUPA lab in France, as well as Mahmoud and Jamal from the Liris lab in France as well. So I will start by introducing the background and research problem. Then I will present the motivating scenario of our work. After, I will detail our proposed solution to underline after the implementation and evaluation phases, and to end with a recap and future perspectives. So to start with the background, the rapid expansion of cyber-physical systems and the technological advances in sensing technologies and data mining techniques have contributed to the tremendous development of smart people-driven applications. These applications reshape the lives of people in many domains by providing advanced services such as increasing their comfort, monitoring patients and elderly, optimizing energy consumption, as well as many other services. These services are achieved or are delivered to the user based on prior collection and processing of massive amounts of data in order to discover the underlying patterns and trends, such as, for example, location data in order to provide location-based services, health data, energy consumption data, and so on. Nonetheless, several privacy concerns hinder the wider use of this data because actually mining and processing data can lead to reveal a wealth of sensitive information about individuals, such as their habits, behaviors, health conditions, activities, preferences, and so on. So we're talking here about sensor data, which are spatiotemporal by nature. So analyzing and processing the patterns traced from this data can lead to entail several privacy risks for users. So such disclosure of sensitive information can be harmful if user data or information is misused by service providers, sold to interested third parties without user consent, or even stolen by cyber criminals, as nowadays service providers are victims for cyber attacks that leads to many data breaches. So on this basis, several works have been proposed in the literature with the objective of balancing or optimizing data utility privacy trade-offs according to the individual situations and or preferences. These works were mainly introduced as privacy models, which may vary from context-aware to personalized privacy models. Nonetheless, these models do not actually, they apply the level of protection on data, but without considering the effect of temporal correlations between data values and their impact on privacy loss. In fact, such a problem takes place when significantly decreasing the level of data protection, which enlarge the precision gap between the sequential data values, and thus this makes the subsequent protected data more precise, which improves the capabilities of an adversary when using advanced mining techniques to reveal the real values of private data pieces that required more protection. So this makes current privacy models vulnerable to data inference attacks, which are data mining attacks, during which adversaries are capable of estimating or inferring the real values of protected data with high confidence. So in order to represent this research problem, we considered the following illustrating scenario. So we consider the scenario of a user, Alice, which is a cancer patient who shares her location data with the remote monitoring platform for cancer care. Alice shares also her location data with several other providers through applications and social media platforms to benefit from their services, such as Facebook, Google Maps, and so on. And she uses a context-aware privacy system deployed on her mobile device in order to protect her data based on her situation and preferences. So the system is capable of providing her with strategies to apply according to her situation and preferences. So if we consider that Alice has a medical appointment at the Belara Ramsey Center for Cancer Treatment, she takes the route from her home to the treatment center. However, locating Alice and the cancer center can entail the disclosure of her health conditions, which involves privacy concerns for her. So consider that the privacy system increases data protection at this transition to 80%. So this transition means that when Alice arrives to the center and then shifts the level of protection to 20% when she leaves. So in this example, we are considering two protection transitions. The first, where the location data protection is increased to 80%, and for the second, it's decreased from 80 to 20%. So the system protects the sense data using a generalization-based function. We consider next the next 3 slides different cases that showcase different behaviors of the privacy preserving system during the second transition phase. So we are focusing now just on the second transition phase from 80 to 20%. So in this first case, we consider that no changes have occurred during this transition changes related to the protection function, and the data are generated in regular time series. So when processing and analyzing the protected data values, an adversary can notice in this case a significant gap in the level of precision between transitional or correlated data. This precision gap limits the range of estimating previous location of the user where protection was critical. It means when Alice were in the medical center, which entails privacy problems to her. So this consequently underlines the need for a gradual descent in the protection level in order to overcome the vulnerabilities that may arise during protection transitions. And in the second case, we consider a change in the protection function. So we consider that the system has shifted the protection functions from the generalization to the randomization method. And in this case, we noticed that both protection methods share similarities because the randomization and the generalization based methods are both belongs to the same category of protection functions, which is the noise addition functions. So this highlights at this stage the need to consider also the protection function dependency and study its impact on the protection deviation rate, because even if we change the protection function, but the protection remain the protection function shares similarities with the previous one, this could also entail privacy concerns and could also lead to data inference attacks. And the third case, we considered, in this case, actually, we considered the case of non-regular time series data, because in the first two cases, we considered the case of time series data where data were generated in regular time series. So we consider in this case here that the system has lost connectivity with the GPS sensor, and the location data was stopped, has not been shared anymore with data consumers for a certain time interval, during which the next or the subsequent attribute data of attribute became independent from the previous one. So in such cases where the time interval is so large so that the subsequent data values are independent, we do not need to, there's no actually privacy problems in such cases, and we do not need to integrate a specific solution in order to protect the system from data inference attacks. So it's also important to consider the measurement of the temporal dependency between data when considering the deviation rate of the data protection level. So based on the before mentioned needs, our objective in this work is to provide a complementary solution to existing privacy models that helps overcome the vulnerability caused by large gaps in data precision. Nonetheless, to achieve this objective and to answer the needs mentioned before, several challenges emerge. The first challenge is related to data dependency. So first, how to track and measure temporal dependencies of sequential data values and how to study their impact on the protection descent rate. The second challenge is related to the protection function dependency. So how to compute the similarity between transitional protection functions and how to adjust the downshifting mechanism accordingly. The third challenge is related more to how to provide a non-deterministic solution, because the protection level can fluctuate between two same values for several protection transitions. This could entail the disclosure of the deviation rate by adversaries if executed process is deterministic, as shown in the figure next to the sentence. So the solution should therefore be non-deterministic in order to overcome the vulnerabilities arising from repeated transition patterns. And finally, the fourth challenge is related more to the performance of and the behavior of the solution. So the solution must be scalable. It means it must handle a simultaneous reasoning over an increasing number of attributes. As well, it should maintain computational and storage efficiency, which increases its usability to also include privacy models which are subject to real-time constraints, and makes it also operational on a variety of devices, including those with limited resources. So to address these needs and challenges, we propose next PSGD, a stochastic gradient descent solution, which intervenes at the protection descent phase and performs an iterative process that measure dependencies between data and protection functions and gradually reduces the level of data protection accordingly. So instead of a direct shifting of the data protection level during protection transitions, we inject a gradual descent process that gradually descend actually or gradually decrease the data protection level during the descent phases until reaching the desired level by the privacy model. So the proposed process is generic and non-deterministic, and it's capable of measuring dependencies between sequential data values and the protection functions, and determining accordingly the appropriate protection level to be achieved for the current data value prior to its release to data consumers. So our approach can be plugged or can be connected to numerous existing privacy models since it's generic, and it ensures as well attribute diversity, so it's capable of handling attributes with different data types and formats, as well as handling protection function diversity, so it can operate with the several privacy models regardless of the privacy protection function that is adopted behind. So before detailing the quantification of the gradient descent process, we start by formally defining some, formally presenting some definitions, but I will just present it in a summary in this presentation, knowing that it's much more detailed in the paper. So we start by defining an attribute. So an attribute has a description, the source from which the data of this attribute are collected, the set of data consumers with whom data of this attribute are shared, the standard time period during which two data values are said to be time dependent, and the log file of this attribute, which includes actually all the data values collected of this attribute with their corresponding metadata set. Then for the protection function, so a protection function is a protection method that can be executed on data values of an attribute. So each protection function has a name, generalization, random noise, differential privacy. In case of anonymization functions, we could have k-anonymity, L-diversity, etc. The category to which this protection function belongs, which could be a noise addition, anonymization, access control, or encryption function. The set of features characterizing the protection functions, such as, for example, the cost, the computational cost of this function, and finally the set of input parameters of this function, which could include the the attribute on which this function is applied, the level of protection that we aim to achieve for the data of this attribute, and so on. The third definition is related to the data protection level, which expresses the amount of protection to be achieved for the data of the attribute. So the data protection level is a probabilistic value. It means, or it expresses the semantic of the level of protection to be achieved for the data. So if P is equal to 0, this means that data is shared in a fine granular version, so no protection is applied on data. And 1 means that data is not shared. It reflects the highest protection level. And a value between 0 and 1 indicates the level, the protection level that should be reached on the data of an attribute when applying a protection, the corresponding protection function on these data. So,
Karan, please try to wrap up in next 2-3 minutes. Yeah,
okay.
We're running out of time. Yeah.
I just bypassed the time. Okay. To summarize our proposal, so the gradient descent process is the proposed gradient descent process is an iterative process that is executed on each sequential data value apart. So the current protection level that should be assigned to the current data value depends on the previous one, on the deviation rate and on the random noise that should be added in order to make the process non-deterministic. So I will just pass quickly to the deviation rate quantification. So the deviation rate quantification is obtained or is quantified based on the similarity between protection functions as well as the temporal dependencies between data values. And in order to measure or to track the dependencies between data values and protection functions, we just before we introduced a transition matrix which will work as the cage of the process in order to ensure the traceability of the data properties of the attributes. So we validated and evaluated our proposal by first developing a Java-based prototype. So we focused on the second transition that was illustrated previously in the scenario. We repeated the descent phases 3 times to emphasize the non-deterministic behavior of the solution in the case of repeated transition patterns. And we considered the regular time series with data generation time of 1 second. So we noticed that the deviation pattern varied between the 3 similar transition cases, as well as the number of data values required to achieve protection convergence. This is due to the noise value associated with the deviation rate, which varies randomly with each iteration. Next, we evaluated the performance of our approach by considering two criteria: the total execution time and the memory overhead. And we formally studied the storage complexity of our approach. So to summarize it, the experiments show that the proposed approach is scalable, efficient in time and space, and maintain effective performance in different scenarios. This increases its reusability to also include privacy models that require real-time reasoning, and allows considering several types of devices, including those with resource constraints. So to conclude, we proposed in this work a privacy-preserving stochastic gradient descent solution that could be connected to numerous existing privacy models in order to provide an additional layer of protection against data interference attacks. So our proposed process features, our proposed solution features a non-deterministic process that gradually decreases the data protection until reaching the targeted or desired protection level. Of course, several improvements still need to be considered. So first, we only considered the time dependency of data in the study, knowing that we aim to extend it in order to further consider the spatial and contextual dependency of data when measuring the global data dependency. So we are seeking to propose a three-dimensional dependency graph that consider time, space, and contextual dependency of data. Then we aim also to improve the protection function dependency procedure to also consider the semantic similarity of the features of these functions. And finally, we aim to connect our PSG data and existing privacy model in order to test its applicability in real-life scenarios. Thank you for your attention.
Thank you, Karam. Let's move to questions and answers. There is one question already from Gamal El-Kumi. Gamal, I will allow you to talk.
Hello. Thanks, Karam, for your presentation, and I've read the paper. It sounds nice. Thank you for that. I have a question about your gradient descent mechanism. So how could the proposed mechanism protect the spatio-temporal attributes with the existence of a schedule? I mean, like, for example, if an individual executes a single activity during a business day.
Yes, actually, if we consider the case of a single activity, and this activity, there's a specific set of data values that are generated and from which the activity is identified. So our mechanism focus on identifying the data protection level to be assigned to these data values. It is only used, if you want, when we consider the protection transition. So, for example, if we consider, just to give an example to be much more clearer, if we consider, for example, a morning activity done by the user that involves two contexts, such as, for example, in the first context, the user is at home. So the second context, the user is in the mall. If the same activity exists in these two contexts, the level of data protection will vary between these contexts because the situation of the user has varied. So the privacy situation as well, the privacy risks incurred from the analysis or the mining of the generated data values. And our proposal intervenes at this stage when the protection level of sequential data values significantly decreases. So we apply this process to gradually decrease the protection level instead of applying a direct shifting of the protection. So it could only use in case of scheduled activities, only if the data protection level varies during the same activity. I don't know if I answered well your question.
Yeah, thank you for your answer.
Thank you, Gamal. Do we have time for one more question from the audience? Do we have any questions? Raise your hand if you have a question. All right, I don't see any questions. Maybe I can make a quick question. So, you know, this is not my area, so my question can be totally silly, but I was wondering if you consider a longer time frame, right? Or that the person visits a certain location again and again, and of course you try to obfuscate it, etc. But cannot you use some mechanisms and from multiple occurrences of those visits to approximate the location, right? Like if I would be an adversarial, that would be my approach, and I would be slowly limiting the number of privacy vulnerable values that are somewhere in the area where the data becomes imprecise, right? That would be my behavior. So maybe you can comment on that. How can your approach protect from that?
Yes, actually, we considered in the study the case of a generic privacy model, regardless of the privacy protection function that is applied behind. So, which could vary from anonymization function to random noise function, and so on. So we consider in the study only the level of data protection that is assigned to the data, knowing that this level reflects the desired level of protection to be achieved on the data when applying this protection function on it. So in case of several data values generated within the same location, if I understood well your question, in case of several data generated in the same location or in sequential locations, the protection function applied will have, of course, its own vulnerabilities that are not considered here, because here we are only focusing on tackling the problem of data inference attacks that could take place when transitioning the data protection level, or when significantly decreasing the data protection level, which makes subsequent data values more precise. And in such cases, the adversary could infer the real values of previous data, which required more protection, such as when we considered the case of the hospital here. So, for example, if in this case the data protection level has directly shifted to 20%, we can easily estimate the real location of the user, which could be in the zone that includes the center. So in case of repeated patterns, so if in case of repeated appointments, this could lead, of course, to other vulnerabilities to consider, which could depend in this case on the data protection level associated to the data values for each of these patterns. And yes, if you want, our objective here was to minimize the gap, the precision gap between the sequential data values. So even if the protection level varies from repeated patterns, between repeated patterns, so even if we consider repeated appointments during the week, the mechanism will always adapt to the transition gap, and will calculate the appropriate deviation rate based on the dependencies between data. So, and of course, based on dependencies between protection functions. So yes, it will be adapted according to the real-time situation, if you want to consider it like that. So it could also consider the repeated patterns.
All right. All right. Well, thank you, Karam. Thank you very much. Interesting work indeed. Thank you for your presentation. I also invite everyone to give a virtual round of applause to all the three speakers. Thank you for filling in the program and this session. So thank you very much, everyone. And this concludes the session. Thank you, everyone, for attending it. We will now have a break, and then we restart in less than an hour now with session 3 and 4. Session 3 will be on process discovery, and session 4 will be on patterns. So have some rest, take a coffee, have some intellectual chats with colleagues, and see you back in an hour. Bye-bye, everyone.
Thank you. Bye-bye.